here for a brief welcoming.
Okay.
And then we will be able to start. We'll also just wait to have some audience already connected. Okay, I think he has some technical problems. So we will have just 1 minute to have some audience already there. And
That's fine.
then we will start, okay?
Okay.
Great. I can see he is there. Hi, Dr. Safian. Do you hear me?
Good evening.
Hi, how are you?
Thank you.
Great. So I'll give you the there. Hi, Dr. Safian. Oh, I have another window open here. So I'll give you the floor so you can welcome Dr. Rector. Okay? Yeah, go ahead. Hello?
Hello. Would you like for me to start?
Okay. So you made a welcoming just on the message box. Dr. Sufyan, do you hear me?
Yes.
Okay. Yeah, okay. Can you please welcome Dr. Rector? We were waiting for you to start.
Welcome to Dr. Rector. Thank you for your acceptance for this conference. I am sorry my English is not very well, but I try to express my recognition to you. Thank you very much.
Well, thank you for inviting me.
Thank you, Dr. Rector. I think we can start now. Okay, let's go.
Okay. Okay. Looks like everyone can see and hear me as well as see the slides that I have. So, hi everyone. My name is Dr. Travis Rector. I'm a professor of astrophysics at the University of Alaska in Anchorage, Alaska. And Nissim was kind enough to invite me to come talk with you. So I'm going to talk about star formation for about 30 minutes. And if people have questions about star formation or anything else related in astronomy, I'd be happy to answer them after that. So one of the areas of research that I work in is how stars form. And so what I'm going to do is talk about how that process works. And one of the things that's really nice about star formation is that there are a lot of beautiful places in the universe where star formation is happening. And so I'm going to share with you some of the images that I've made over the years of these places. So the first thing to know is that outer space is almost but not completely empty. There is dust and gas out there. And so when we look out at the night sky, even though it looks like it's empty, there is material out there. And that material is about 70% hydrogen, 28% helium, and just about all the other elements out there are 2%. So hydrogen and helium are the two lightest elements on the periodic table, and they're also by far the most abundant. So when stars form out of this material, that is the material they form out of. Now, of the material that is out there, some of it is in the form of dust. Now, when we think of dust here on Earth, we think of that very fine, dark material that settles on our furniture and in our homes when we haven't cleaned in a while. And so the dust that's out of space is very similar to that, but is actually even smaller. So dust is very important for a variety of reasons. It is a fundamental building block in building structures like planets and asteroids, but it also has important effects on the light that we look at when we use our telescopes to look out in space. So dust absorbs shorter wavelength light, like blue light, and it absorbs it more effectively than it does long wavelength light, like red light. So one of the techniques we use is to look at a type of light that's called infrared light. So infrared light is a form of light that is longer wavelength or lower energy than what our eyes can see. Now, the nice thing about infrared telescopes is they allow us to see through the dust. So many times the things we look at are invisible using optical light, the light that most telescopes use. But when you use an infrared telescope, you can see it. So just for a comparison, these two pictures show the constellation of Orion. The picture on the left is the kind of picture you're probably accustomed to seeing, where you see the constellation itself. The picture is dominated with little dots that are stars. And you'll notice just below the center of the image, there is a little red area, and that is called the Orion Nebula. Now, if you look at the same portion of the sky using an infrared telescope, you see what is shown in the picture on the right. And so notice now you can see that the sky is glowing, and that glowing is coming from dust that is out in space. So what's really nice about using an infrared telescope is it allows us to see the universe in a different way. Now here's another comparison. This is a picture of a star-forming area called the Elephant's Trunk Nebula. And when we look at it with an optical telescope, you can see that there's areas in it that are opaque, they're dark, and we can't see what's inside. But if we use an infrared telescope, this is a picture taken by the Spitzer Space Telescope, a NASA infrared telescope, you can actually see that there are stars embedded inside the elephant trunk. So the really nice thing about infrared telescopes is they allow us to see what's inside these clouds of gas. So when you see these pictures, you'll see all these different colors, and I wanted to take a minute to describe what the colors correspond to. So you have these giant clouds of gas in which stars are forming, and these clouds of gas are illuminated or lit up by the stars that are in and around the cloud of gas. Now, when you look at these pictures, you'll often see that they are reddish in color, and that is because these clouds of gas are made mostly of hydrogen gas, and when hydrogen gas is warm, it produces a specific color of red light called hydrogen alpha light. This is a color of red light that is just right on the edge of what our human eyes can see. And so that is a color you see in many of these images. Now, also when you look at these images, you'll notice there's areas that are darker, and these are areas where there's dust that absorbs the light from the stars behind it. And in many places, you will actually see the dust looks blue because dust can scatter light as well. It's the same reason why the sky is blue during the daytime. So here are some pictures showing different examples. So if you look at this picture here of this star-forming region, you will see that it overall has a bluish color, and that bluish color comes from dust that's inside the gas, and that dust is scattering blue light from the hot blue stars that are in and near this gas. But if you look closely, you'll also see little red areas, and these are areas where there is warm hydrogen gas that is producing that hydrogen alpha light. Here is another example. Now this is, if you look closely at this picture, you'll see that this bluish cloud of gas, which kind of looks like a mushroom, it is blue because it is scattering the light from the stars that are surrounding it. But if you look near the center of the mushroom, you'll see that there is a sort of a yellowish orangish star there as well. And that's because the light from that star, as it passes through the dust takes away the blue light and just lets the orange, yellow, orange, and red light to go through. And that's why it looks that color. Here is another beautiful example. This is a nebula called NGC 1333. And in this picture here, you can see the bluish scattered light near the top. And then if you look at the bottom, you can see that there are these reddish blobs. And in a minute, I'm going to talk about what those reddish blobs are and why they're important. Now here's another picture. This is of the famous Horsehead Nebula. And in this picture here, you can see that we're actually looking at the edge of a cloud of gas. And the way you can tell that is if you look at the top half of the image, you'll notice that you can see many stars, and you can see many more stars than you can see in the bottom half of the image. So in the bottom half, we are looking into a cloud of gas, and it is blocking the light from the stars that are behind it. So I'll just share with you some more beautiful images. So one of the things that's really nice about these star-forming areas is that they have these beautiful structures, and that is because of the complex clouds and all the stars that are embedded around it. So this is a famous nebula that's called the Catalpa Nebula. And I'll just share with you some more pictures as well. Now in these pictures, you'll notice that they have a nice orangish or reddish color, and that comes from the hydrogen alpha light produced when the hydrogen gas inside them are warmed up. Now in this case right here, you can see these dark areas here, and these dark areas are called Bok globules. Bok was a famous astronomer who did research in how stars form, and each of these little dark areas is black because it is blocking the light from the stars and gas behind it. And these dark areas are areas where stars are forming. So with the Hubble Space Telescope, we can zoom in on one of these Bok globules. And in this picture, I have shown here the size of the cloud of gas, just to give you perspective. It's about 1 light year across. And each of one of these small globs has about enough gas in it to make 2 to 5 stars that are the mass of the sun. Now, in each of these little clouds of gas, you can actually make more than 1 star. And most stars that are formed are actually masses less than the sun. And so even in a cloud, even in one of these small clouds, you can make many stars. So these dark areas are called molecular clouds. And these are clouds where the gas is cold enough that the atoms can actually stick together, and gravity will be able to overcome the particles and cause them to start clumping together. So what I'm going to show you now is a computer simulation. And in this computer simulation, what you're seeing here is a red circle. And this red circle might look like it's actually a star. Maybe it's like a red giant star. But actually what this simulation is of a cloud of gas. And this cloud of gas, as it collapses, you're going to notice that it's going to form into many different clumps. And each of these clumps is going to form multiple stars. And these stars will appear as white dots. And I just want you to watch and see what happens to those stars after they form. So you notice the cloud of gas begins to shred. And in just a second here, you'll start to see these little white dots appear. So these white dots are the stars as they form. If we zoom in here, it'll be easier to see. Hopefully this is all visible to you. Hopefully the video's quality. So if you look near the center, you'll see these white dots starting to appear. Now, one thing I want you to notice is that some of these stars are actually moving very fast. So when a large cloud of gas, like this one, forms stars, some of the stars will actually be ejected. They will be thrown out of the cloud of gas at high speed because of the gravitational interactions they have with other stars nearby. So as the simulation plays out, you'll see that there's actually hundreds of stars that are being formed. And while most of the stars stay within the cloud of gas, many of the stars are being shot out at high speed. So after the simulation is done, you can look and see that you can see now that hundreds of stars have formed out of this cloud of gas. And you can see that there's still remnants of gas left over, which is shown as the red light there. Okay, so we can actually see these stars being shot out of clouds of gas. And in this picture right here, which I helped to make, you can see there are stars being shot out at high speed. So what you're seeing here, these streaks, you'll notice at the end of each of these streaks is a little blue dot. And what this is the bow shock or the wake left behind after a star has been shot out of the Orion Nebula at high speed. So as I mentioned before, we can use infrared telescopes to see what's going on inside these clouds of gas. And so this is a picture of a dark cloud of gas where when we look at it with an optical telescope, we can't see inside. But when we look at the same cloud of gas with an infrared telescope, we can actually see there are stars forming inside. And the stars that we're particularly interested in are the redder ones. And the reason why is these are stars that have a warm disk of material swirling around them that is the early stages of the formation of a solar system. So that red star near the center of the image is a place where we think planets may eventually form out of the disk material swirling around that star. Here's another example. This is a dark cloud of gas that invisible in the visible light, the light we see with our eyes, we can't see inside. But when we look with an infrared telescope, we can see through and see what's inside there. So when it comes to the formation of stars, there are several stages that happen. The first is that you have this large cloud of gas, like the simulation I showed you, and gravity causes that cloud of gas to start to collapse. And as it collapses, the gas starts to heat up. And there's two ways to think about it. The first is that as the atoms are falling in from gravity, they will start to speed up, so they will become hotter. Another way to think about it is if you've learned in an introductory physics class, you may have learned about the ideal gas law. So in the ideal gas law, if you squeeze the gas, if you compress it, the gas will become hotter. Now, these little clumps that form are what are called protostars. So these are stars that are in the process of forming, but haven't actually turned into a star yet. Now, each one of these little clumps will be rotating, and because it is rotating, the gas will collapse into a disk around the protostar. And this disk is material that will fall into the black hole, and not the black hole, but into the protostar to make the star bigger. But some of the material will also be shot out as jets of gas along the axis rotation of the protostar. So this right here is the artist's conception of what that actually looks like. So what you can see here is that you see embedded inside this dark cloud of gas is a protostar at the center, and there's a disk of material swirling around, and some of that material, instead of falling into the protostar, is ejected along the axis of rotation in these jets. So when we look at pictures like this, all those little red lines that you see sticking out of the nebula, are those jets of gas. And these jets of gas glow red because they are made of hydrogen, and they are moving quite quickly. So you can see in this case, you can see these jets of gas popping out of the dark cloud of gas. These outflows can pop out of the gas. So these red areas are called Herbig-Haro objects, named after George Herbig and Guillermo Haro, who were the two astronomers back in the 60s who first discovered these objects. So the work that I do is searching for these Herbig-Haro objects as a way of finding forming stars. And the reason why these Herbig-Haro objects are useful is because these jets of gas can poke out of the dark clouds of gas and show us where stars are forming inside. Here are some other examples of Herbig-Haro objects. So this is an area of gas. And if we zoom into that square in the upper right, we will see a Herbig-Haro outflow. So that red line that is coming out of the star is a jet of gas that is being shot out from that protostar. And even though you can only see the jet in the bottom half, there's actually two jets, one going up and one going down. And you'll see these little sort of green crescent shapes. And those are what are called bow shocks. And those are produced when the jet of gas collides with the interstellar gas nearby. And this produces what's called a shock, because the gas is moving faster than the speed of sound. When it collides with the gas, it produces an effect like a sonic boom. This is known as a shock. So here are some other examples of Herbig-Haro objects. Again, jets of gas that are being shot out from protostars. And here's a picture of one shown in the infrared. So the common thing you see in these jets of gas, these Herbig-Haro objects, is that there will be a protostar at the center, and there's one and sometimes two jets of gas that are being shot out. So the research I do is to look for these objects, and what I do is I use telescopes at various observatories, including Kitt Peak National Observatory in near Tucson, Arizona, the Cerro Tololo Inter-American Observatory in Chile, and Las Campanas Observatory, also in Chile. And using these telescopes, I take high-quality images of star-forming regions, and I look to see if we can find these Herbig-Haro objects. So this is an example. This is a nebula called NGC 7023, otherwise known as the Iris Nebula. And if you look at it, you'll notice that it's mostly blue from the scattered light coming from the bright star in the center of the nebula. But if you look closely, you'll notice that there are little red blobs. And so if we zoom in, you can see these little red blobs in and around the nebula. And so these are the Herbig-Haro outflows. And they can be very hard to see because their light can be obscured, at least partially, by the dust and gas in the nebula. So here's a color image of those objects. If we look in black and white and just look at the hydrogen alpha emission, you can see that there are several of these Herbig-Haro objects in there. And there is a plus sign there that indicates the location of what we think is the protostar, that is the object that is producing these jets of gas. And there's actually two jets of gas, one that runs horizontally and then one that runs vertically. And if we use the Spitzer Space Telescope, the infrared telescope, we can look inside there and we can see there's actually a cluster of protostars, also known as YSOs or young stellar objects. And so one or more of these stars is producing these jets of gas. So how long does it take for a protostar to become a star? Well, a star becomes a star when the center of it becomes hot enough for nuclear reactions to occur. The way that most stars, including the sun, produce their energy is the nuclear reactions that turn hydrogen gas into helium. And while a star is doing this, it is known as a mean sequence star. Now, high mass stars form faster than low mass stars because the more massive The more gas there is, the stronger gravity will be, and the faster gravity can pull the gas together to form a new star. So it took the sun about 30 million years to form. In comparison, a star that's only 0.1 or 10% the mass of the sun would take about 100 million years. So it would take about 3 times longer. Now, in comparison, a star that is 10 times the mass of the sun would only take about 100,000 years. So these stars form much faster. And in fact, these high mass stars will form, live, and die before the sun is actually a star that's the mass of the sun will actually have formed. So this plot right here shows how long stars live their lives. And the more massive the star, the more luminous it is. And so you might think that more massive stars would live longer because they have more gas inside to turn into from hydrogen to helium. But actually, these high mass stars don't last very long at all. So for example, if you have a star that is 100 times the mass of the sun, it has 100 times the gas, but it is 10 to the 6th or 1,000,000 times brighter. So that means that its lifespan is only 1/10,000th that of the sun. So to put that in perspective, if our sun were like a normal human lifespan of about 80 years, a star that is about 100 times the mass of the sun would live for less than 2 weeks. So these high mass stars live for a very short period of time. So once these stars form, the energy from the star will blow away the gas surrounding it. Now, the high mass stars produce so much energy they can actually blow away the gas that's surrounding other protostars. And then the energy from these stars can hollow out the cloud of gas in which they form. And so I'm going to share with you some pictures of this taking place. So what you're seeing right here is a picture of a star that's forming in a cloud of gas, and that the energy from that star has just caused it to poke a hole in the cloud of gas. What we're seeing in this picture is the light shining through. So it's sort of like if you have a small bird in an egg, like a chicken, or a hen inside an egg, and the hen has just poked a hole through the egg with its beak. Here's another example of that same thing going on. And here we see a star at the center that is slowly blowing away the gas that is surrounding it. And here's just some more examples of that as well. So in all of these pictures, what's happening is you have one or more stars at the center of the nebula, and the energy from those stars is blowing away the gas surrounding it. Now, in the case of this picture, which is called the Eagle Nebula, there are several very massive stars, and the intense energy those stars are producing is carving out the center of these nebula. So this is the Eagle Nebula. Here's another famous nebula called the Rosette. And in all of these cases here, you can see that there are multiple stars at the center of the nebula which are hollowing it out. Now, stars can appear in a range of sizes. To be a star, that is, to be massive enough to have nuclear reactions, the star must be more than 8% the mass of the sun. Otherwise, it will be too small and will be an object that's called a brown dwarf. Now, if you try to make a star that is too massive, the star will produce energy so rapidly it will start to blow itself apart. So stars can't be more than about 100 to 150 times the mass of the sun. If they start off more massive than this, they will quickly blow away that mass. And the stars that do this are called Wolf-Rayet stars. So here are some pictures of Wolf-Rayet stars. These are very high mass stars that are rapidly losing mass through the intense nuclear reactions occurring inside the star. So here's just some different examples of this. So in each of these cases, what you're seeing is the nebula produced as the bright, hot blue star at the center is blowing off the gas around it. So which stars are the most common? Well, it turns out low mass stars are much more common than high mass stars. So for every star that is more than 10 times the mass of the sun, there will be about 10 stars that are in the range of 2 to 10 times the mass of the sun, about 50 stars that are around the mass of the sun, and then over 200 stars that are less than half the mass of the sun. So compared to most of the stars out there, the sun is more massive than most. So all of these stars go through the same process in formation. It's just that the high mass stars form much faster. So I've been talking for 30 minutes now, so I will stop there with my presentation. So if there are questions that people have about anything from my talk or just astronomy in general, I will be more than happy to answer them.
Thank you very much, dear professor. It was really an amazing presentation. The photos you have showed were really fantastic.
Thank you.
It's not my expertise or my specialty, the astrophotography, but even for a person from a biology background like me, it was really amazing. Thank you. Do you have something to add, Dr. Cocoon, before I forward the questions from the audience?
I have some questions
Great.
about the relation between the mass and the luminosity of the stars. What is the method to do for the determination of this relation?
So the energy produced by a star is dependent on the rate of nuclear reactions occurring in the core. And the rate of nuclear reactions is extremely sensitive to the temperature and pressure inside the core. And there are many different types of nuclear reactions that occur inside the star. There are multiple pathways for turning hydrogen into helium. And when you have more massive stars, or when you have stars later in their stages of life, they can produce energy in different ways as well. So the way that there's different ways of determining the mass of a star. We, of course, can directly measure the luminosity. And then we also know the effectiveness of nuclear reactions based in large part on the research that's been done for the development of nuclear weapons. So ironically, it's a peaceful use for that knowledge.
Okay, thank you. My second question is about the Herbig-Haro objects.
Mm-hmm.
These objects are associated with eruptive variables as FU or Orionis or T-Tauri variables?
So they are associated with variable objects, but these Herbig-Haro outflows tend to occur in objects that are younger than FU Orionis stars. So this is an earlier stage in the formation of the star.
Okay, thank you.
Okay, these were all your questions, Dr. Moon?
No.
Okay, I will start.
Okay, thank you very much.
I will start by asking the questions from the audience. We will start by Ariadne Gallardo, who asked, what kind of gas and dust is more common there? I suppose by there she's talking about space.
So, as I said at the start of my talk, the most common gas is hydrogen and helium, and the dust is made up of compounds like carbon, nitrogen, and oxygen. So these are molecules that are sticking together to form into what will eventually be the material that can form into protoplanetary objects like asteroids and comets and things like that. So the material that's in these nebulae is essentially the same kinds of material that we have in our solar system.
Great. And another second question from the same person. She asked, the constellation of Sagittarius has a nest of baby stars, but what is the more close to us?
So in the direction of Sagittarius, that is in the direction towards the center of our galaxy. And so it's a very complicated environment to study because you're looking in the direction of so many stars and areas where stars are forming. So one of the nearest regions to us for star formation is the Orion Nebula. And because of that, it's a very well-studied region.
Okay. She also asked, what is the most dedicated telescope for stargazing? And this is the last question from Ariadne.
Oh, I'm sorry, could you repeat the question?
Okay, she asked, what is the most dedicated telescope to stargazing?
Oh, I don't really know how to answer that question. Is she asking about, like, what is the best telescope for stargazing, or just what do we professional astronomers use, or?
I can't guess really what she meant, but maybe what the most dedicated, maybe the telescope who is mostly working on observing stars, but not dark matters or other stuff in space.
Okay. So there are many different types of telescopes, and all of the different telescopes that we have, some are particularly good for certain areas of research. So, for example, radio telescopes are very good at studying objects like quasars and radio galaxies, and also places where stars are forming. So each telescope has a different strength as to what kinds of things it can do. So astronomers, for the most part, use many different kinds of telescopes, and they use whichever one is best suited for the kind of research that they want to do. So there's not one particular telescope or one type of telescope that's the most useful, because each telescope does a different thing. So it's like having many different kinds of tools, whether you have hammers or a saw or a screwdriver. Each one is good for a particular purpose.
Okay. We have a question from Shaima Biba. She said, we all know that in a globular cluster, nearly all the stars have the same age. But what will happen if they die at the same time?
So whether it's an open cluster or a globular cluster, the stars for the most part form all at the same time. But how long a star lives depends primarily on how massive it is. So high massive stars will die much more quickly than low mass stars. So when you look at a cluster of stars, whether it be an open cluster or a globular cluster, you can actually determine how old the stars are by the masses of stars that are there. When you have a young cluster of stars, it will have high mass stars and low mass stars. But older clusters of stars don't have high mass stars because those stars have already lived and died. So we can actually tell how old a cluster is by how massive a star we can find in it. So I know that's not quite what the question was, but the important thing to know is that the stars don't all die at the same time.
Okay. Another question from Mr. Hisham. It's about the sun. It's about our star. He asked, where is the accretion disk of the sun?
We're living on it. So the accretion disk is no longer here. But in the accretion disk for most stars, you will have clumps of material that will eventually form into planets. And then once the protostar becomes a star, the energy from that star will blow away whatever dust and gas is left over. So the planets in our solar system and the asteroids and comets all formed out of an accretion disk that was swirling around the sun billions of years ago. And those objects, some of those objects, collided with each other to form into more and more massive objects. So we no longer see an accretion disk around our star because the material is all formed into planets or other things.
Okay. Next question is from Mr. Ashraf Toumi, who asked, can we attend a visible star death in the next few years?
Well, we don't know. We might see a star explode as a supernova in our galaxy. That's something that can happen. A star in a galaxy as large as the Milky Way, a star explodes as a supernova roughly once every 50 years or so. It's actually been several hundred years since we've actually been able to see one, but it's possible that one could have exploded on the other side of our galaxy and we couldn't see it. So it would be amazing. That's something I hope that I get to see in my lifetime, is to actually see a supernova that explodes in our galaxy and we can actually see it with our eyes. But we have no way of knowing when exactly a star will explode. There's many stars that we know are very close to dying, and they may explode as supernovae within the next 1,000 years, but we don't know whether it's tomorrow or next week or in 5 years, 10 years, or 20 or 200 years. We don't know. We can't know accurately enough when it'll happen.
Okay, I think so. This applies also to the Betelgeuse star. There was a lot of speaking about it because its brightness was decreasing. And we have a question exactly about this. We have Mariam who asked, are we going to see the supernova of Betelgeuse any soon? And can you describe for us what are we going to see from Earth if this happens?
So we don't think we will see Betelgeuse explode soon. Again, it may be within the next 1,000 years or a couple of thousand years. We don't know exactly. Betelgeuse became fainter because it is a red giant star, and these red giant stars can have darker areas in the star. The outer part of the star can change shape, and they can temporarily become fainter. So if we did see Betelgeuse explode as a supernova, it would be bright enough that we could see it during the daytime. And so that would be pretty amazing to see. It wouldn't hurt us. We're not at risk of being harmed if Betelgeuse exploded as a supernova, but it would be bright enough we could see even during the daytime.
Okay, great. I think we have more questions. If you still have time, professors, we have people that are interested here. Ask questions.
I do. I have about 15 more minutes.
Okay, great. Perfect. So we have Ashraf also who asked, is there a relation between star formation and dark matter?
Is there a relationship? Not on small scales. So when a disk of material is forming around a protostar, dark matter and dark energy are not important in that process. But dark matter and dark energy are very important in the formation of galaxies and the clouds of gas inside them. So dark matter and dark energy do play indirectly an important role in making it possible for clouds of gas to form stars. But what actually happens inside the cloud doesn't depend much on either of those.
Great. I have a question from Mehal. She's asking, this is a little more general, but what are the latest techniques used to better detect the different kind of rays coming from space with radio telescopes, for example? And how do we minimize the noise since we have, it's not clear here what's written. Just 1 second. Oops. Since we have many satellites, rotating around the Earth, and what should we focus on detecting right now?
Well, that's a very good question, because one of the concerns we have in astronomy is that as more and more satellites are launched into space, these objects can interfere with our observations from Earth. And when an astronomy picture is taken, an astronomical picture is taken, sometimes we will see a streak of light across it because a satellite has passed across the image while the picture was being taken. And usually what we'll do is we'll take multiple pictures of the same area, and then using computer software, the software will figure out which part is from the streak, and it will remove it. So in some cases, we're able to compensate or overcome the effect of the satellite. But especially in radio astronomy, where more and more satellites are being launched to do radio signal communications, like for internet or for satellite phones, those will affect the radio telescopes more and more. So the good news is right now, we are able to use computer software to overcome or remove the effects of these satellites. But if there are thousands of these satellites, then it can become too much for us to overcome. So we do have a big concern in astronomy right now that these satellites will make it hard for us to do our work.
Okay. A question from Mr. Abdel Hafid. He says, what causes or initiates the rotation of stars around themselves and the rotation of their disk?
So you have these giant clouds of gas out in space, and these clouds of gas will all be rotating maybe very slowly. But what happens is as the cloud of gas collapses and becomes smaller, it starts to spin faster. And this is a physics concept called conservation of angular momentum. If you've ever watched a figure skater spin, as the figure skater is spinning, if he or she has her arms out wide, he or she will spin slowly. But as they pull their arms in, they will start to spin faster and faster. And that's what happens with these giant clouds of gas as well, is that when they're very large, they're several light years across, even if they're rotating very, very, very slowly, as the cloud of gas becomes smaller, it will start to spin faster and faster. So if you look at our solar system, almost everything in our solar system rotates counterclockwise around the sun, and almost everything turns counterclockwise. And that's because the large cloud of gas out of which our sun and solar system formed was initially a cloud of gas that was rotating very slowly counterclockwise.
Okay, great. We have a question from Khadija. She's thanking you for this presentation, and she's saying, what about the hypervelocity stars?
What about them? Well, they're very interesting objects. So these are objects that can, because as I showed in the simulation, as the cloud of gas collapses, these stars are shot out at very high speeds. These stars can be going fast enough that they can actually be shot out of our galaxy. They have enough speed to achieve what's called escape velocity. So that is, they will be shot out of our galaxy and not return.
Okay, I have a curious question from Mr. Mohammed Mahdi Batif. He's asking, can somehow a black hole transforms back into a star?
No. Once an object is a black hole, it cannot turn back into a star. In fact, for the most part, black holes just simply become bigger and bigger as they absorb material around them. So unfortunately, it cannot go the other way around.
Great. I think I'm about to have just the final questions. So which one to select? Yeah. There is a person called Rushra. He's asking, or she's asking, are stars beneficial in any way? What's their role, and what would happen if a star died?
Well, stars are very important for the origin of our solar system. So our universe has existed for about 13.8 billion years, and the planets in our sun have existed for only about 4.5 billion years. So what that means is there was about 9 billion years or so before our solar system formed, and the metal and rock and all the materials other than hydrogen and helium that are here on the Earth formed inside stars that lived and died before our sun and our solar system were formed. So stars are absolutely critical for forming the elements out of which our planet was formed. And if a star dies now, after our solar system has been formed, it doesn't really affect us in any way. But stars that lived before our solar system formed were very important for us to be here today.
Okay. The person called Mohammed Cortas, he's asking, just to have more details, according to the doctor, just to have more details about the phenomena called V404 Cygni.
I don't study that star system, so I'm afraid I don't know anything about it.
Okay. So the last question is not about really the scientific side of the presentation. It's about your career. The person called Fatin, she's asking about your educational background and how you end up by being a professor in physics and astronomy.
Okay. So when I was young, I loved all of science. When I was very young, I was very interested in chemistry. I thought I would be a chemist. And then I became more interested in physics and astronomy. And I learned that astronomy now is largely what's called astronomy is really astrophysics, which is using the laws of physics to study astronomical objects. So I went to college and earned a bachelor's degree in physics. And then I went to graduate school to specialize in astrophysics. And that's the field that I earned my PhD in. So my PhD, my research was on studying what are called quasars. And since then, I've moved on to do other areas of research, including star formation.
Great. So, do you have, Mr. Kamoun, any question or any remark to add to this presentation? We cannot hear you. Maybe you have muted your... yeah, I can see that your microphone is muted.
Okay,
Yeah, it's
okay.
now.
Perhaps I have a response about the variable star V404 Cygni. It is a compact X binary in the constellation Cygnus, and we think that one component is a compact star, perhaps a black hole. That is my response about this variable star.
Okay.
Then
we have answered all questions today. Everyone is happy.
Then I am very grateful for Professor Rector. Thank you for a brilliant presentation. And I asked Tunisie if you have any other comment or question.
I think it's okay for me. I think I forwarded all the questions from the audience. I want also to thank you so much, Dr. Rector, for accepting my invitation to make a presentation for us. It was very rich, and I hope also that the audience appreciated it. But at least I think as they asked so many questions, I am sure now that they appreciated the content.
Well, thank you very much, Nisam, for inviting me. It was a pleasure to talk with you all. I will mention that I am on Facebook, and you can follow me You just search for my name, Travis Rector, and I post many of the color astronomical images that you saw in the talk are ones that I have made as part of my research or otherwise. And so I share many of these pictures if people would like to see more of them.
Okay. Do you participate in any nonprofit activity that we can maybe promote on our social media, so the students or the persons that are interested in your astrophotography activity, they can go and visit your website or?
So they can visit our website. I will also mention that a few years ago, I co-authored a book called Coloring the Universe. And it's about how many of these astronomical images are made. So that's something that people can look for as well. So it's called Coloring the Universe.
Okay.
Yes.
Okay. I will take a note of this and we will share it with our team members. Coloring the Universe.
Mm-hmm.
Okay. Then I think we are done for today. Maybe we plan in the next future another presentation. So
I'd
I
be
will
happy
keep you
to do so.
informed, everyone. Thank you very much. You're very kind. So I can tell you, everyone, bye-bye. Have a nice day, because I think in Alaska you just started your day.
Yes, it's early in the day here. So thank
And
you all.
good
And
night to everyone else here.
Okay. Have a good night. I'll talk again soon.
Thank you. Bye-bye. Ciao.
Bye-bye.